Hi, welcome back to Calculus. Today we're looking at section 4.6, Applied Optimization. Basically, applied optimization problems are finding max and mins in story problem form. So I'm sure that's exciting, but it also should be kind of nice. We know what to do for max and min problems, right? We find critical points and we test critical points and endpoints to see which one wins. What's the biggest, what's the smallest. So I have outlined here some steps that you can go through to try and do these. First, read the problem. What do you know and what are you trying to find? Okay, these are important things to have in your mind. We want to know what we already have, and we want to know what we're looking for. Step 2, draw and label a picture. Sometimes you can get by without the picture, but it's really quite helpful, as we'll see in the two examples that I'm going to do. Step 3, assign some variables. Give letters to the things you don't know. 4, write an equation. And 5, test critical points and take a derivative so you can test critical points and endpoints. So we're going to, I guess I should have put the derivative in there. That would have been good. Take a derivative, find critical points, then test critical points and endpoints. And finally, answer the question. So let's get started. This will be fun. I've got 2 really nice examples, and hopefully this is good. All right, so here's my first example. It's going to take up more than this board, so in just a minute after I talk you through some of this, I'm going to erase this left-hand side of the board so I can finish the problem. So if you might want to get some of this written down. It says a cereal box needs to hold 1,000 cubic centimeters of cereal. If the bottom of the box is to be a square, find the dimensions that will use the least cardboard. So we want to minimize the amount of material that's used to make this box. Now we have one very important constraint here. The bottom is going to be a square. So if you draw the box, and I have this really lovely picture down here, normally we would label a length, a width, and a height for a box, but here we know that the bottom is a square, so I labeled both of those dimensions with L. That's really nice. It takes away a variable or a potential variable, and so that's going to be good for us. The volume we know is 1,000 cubic centimeters, and that's equal to L squared times H, right? Length times width times height, but since the length and width are both L, we have L squared. Now, I went ahead and solved for H, and we'll see why in just a second, okay? But that means that H is equal to 1,000 over L squared. Again, this 1,000 is because we have a known volume for this box. So what's nice is we're going to be able to use this little teeny volume equation to substitute in for H in the equation we really are going to care about here. All right, so hang on to that information. Let's go over to the other side of the board. The equation we really care about is the surface area of this box. Okay, surface area is going to be the cardboard that's used. So that's what we need to minimize. So if you look at your box, it has a top and a bottom, both of which have an area of L squared. So that's where this 2L squared comes from. And then if you go around the sides of the box, there are 4 of those, and they each have dimensions of H times L. Or I wrote it as L times H, so we have a 4LH. Now we want to minimize this, but with 2 different variables in there, that's a bit problematic. So this is where that volume piece comes in. We know that the height is equal to 1,000 over L squared, and so I plugged that in. I was able to simplify that just a little bit. The L cancels with one of the L's on the bottom, and 4 times 1,000 is 4,000. So I got the surface area formula down to 2L squared plus 4,000 over L. So this is what we need to optimize, and that's what we're going to do. So to do that, we take a derivative, and then we're going to find critical points, and then we're going to test critical points and endpoints, and we'll talk about what those critical points and endpoints could possibly be here in a second. So we take the derivative. The first part's straightforward. We drop the 2 down. 2 times 2 gives me 4L. I have a minus, or I get a minus because I have an L on the bottom here. Remember, this is like having an L to the negative 1, right? Dividing by L and L to the negative first power are really the same thing. So I do a negative 1 times 4,000. There's my negative. But the power goes down by 1, which makes it negative 2, so that's where this L squared comes from. And then because I can kind of see where I'm going to be heading with this, I turned this all into one big fraction, so I just multiplied the 4L by L squared over L squared to get 4L cubed minus 4,000 over L squared. So this is where I have to pause, and we'll come back here in just a minute after I clear off the side of the board and get some more stuff up there to talk about. All right, so this problem actually ends up really pretty simple and interesting once we get here. I can set my derivative equal to 0, and if I do that, we get critical points either if L is 0, because the L squared is 0 on the bottom, or if the top is equal to 0, you can solve that and get that L is equal to 10. Now, the only other possibility here is this. We can make, let me back up. L cannot possibly be any smaller than 0. That's not ever, technically the length can't even be 0. Okay, and so we'll come to that in just a second here. But not only can the length not be 0, or is that the smallest really even kind of meaningful value for the length, but the same is true for h. So if we come back to our volume equation, if we make h get really, really small, L is going to get close to this square root of 1,000. But again, it's kind of meaningless there. Yeah, long story short, yeah. The 10 is really the only one that works. That's kind of what I'm really trying to get at here. You're gonna have a parabola that's, well, you're gonna have something that's upside down. Anyway, so L equals 0 is meaningless. L equals square root of 1,000 is meaningless. The 10 is really the only one that works. And if you plug in 10 for L, you also get 10 for the height. Turns out a cube is the most efficient way to make a box. So anyway, that's our surface area problem. All right, I have one more that I want to look at. This one's kind of goofy and definitely a bit of a mess. So hang on. All right, so here's my next and last example for applied optimization. There we go. A rectangle is to be inscribed under the arch of the curve y equals 4 cosine of 0.5x from x equal negative pi to positive pi. So we want to know what dimensions will give the largest area and what is that area. I drew the picture here. We all are hopefully familiar with a basic cosine curve. It hits 1, which I guess I could have labeled, well, it's not going to be 1, it's going to be 4 because of the 4 in front. It's going to hit 4 here when x is 0. And at negative pi, the function will have a value of 0, and at positive pi, the function will have a value of 0. So basically, we're going to try and squeeze a rectangle into this curve where these top corners are points on the curve. Okay, that's what needs to be inscribed. So from that, I can think of it this way. This point would have an x value, and that would be the length of half of my rectangle. But this is going to be symmetric because the cosine curve is symmetric about the y-axis. So both of those lengths are x, which means that the length of my rectangle is 2 times x. Well, if we have an x value, we get a value for the width here because that's just going to be the function value at x. Remember, this point is on the curve that we were given. So the width is going to be 4 times the cosine of 0.5x. And so now our goal is going to be to put together a formula, or an equation rather, that we can take a derivative of in order to maximize this area. So I think the area function is going to be pretty obvious here. It's length times width because we're working with a rectangle. So remember, we're just using the curve here to really give us those width values. And so that's kind of nice. So let's get this board cleared off and I'll move on with the problem. All right, so let's finish up this problem. Our area formula, using the length and width that we found on the last board, is 2x, that's our length, times the width, which was 4 cosine of 0.5x. Means that our area formula, when we clean that up just a little bit, is 8x cosine of 0.5x. When we take its derivative, we have a product rule and a chain rule, so we have to be really careful. First, the product rule, I took the derivative of the first piece, the 8x, that's just 8 times the second piece, that cosine of 0.5x, plus the 8x, that first piece, times the derivative of the second. And this is where that chain rule is going to come in. Derivative of cosine is negative sine. Oops, that should be around there. That would be better. Where did I put my marker? I don't even know. All right, I lost my marker. That's interesting. Oh, there it is. And let's put the parentheses there. There we go. So minus the sine of 0.5x, but then we have to have the derivative on the inside, which gives us a times that 0.5. So cleaning it up, the derivative is equal to 8 cosine of 0.5x minus 4x times the sine of 0.5x. We need to set that equal to 0, and so I did that. But what you might notice here is that that is disgusting. Okay, you are probably not going to solve that very well. Honestly, neither was I. So I used my calculator. The first thing I did was I typed it into my calculator in the y equals menu. I'm going to be graphing that. So you can see that then I hit graph, and I get a graph. And remember, we just want x to be basically between 0 and pi. Okay, our interval was from negative pi to positive pi. And so we just want x to be somewhere between 0 and pi, because a negative value for x, that would just be, figuring out the left side of the rectangle. But remember, we have symmetry. So we're just going to use positive values for x here. All right, so if you set it equal, or if you graph it, you can hit the second and then the trace button, and then you'll notice then that the second option on there is to find a 0. There we go, that's a little better. So you hit 2, it wants a left bound and a right bound. So what you do is you take that little flashing cursor, so it wants a left bound first, so I'm going to make it just a little bit on the left-hand side of the 0 I want. I hit enter. And then it wants a right bound, so I take it down just a little bit to the right-hand side and hit enter. Then it wants a guess, so I get it as close to that 0 as I can. I hit enter, and you can see then that the x value is about 1.7. So there we go. We get an x value of 1.7. We should probably test. Well, here's the thing. Our interval really from that graph is from 0 to pi. But the problem is this with those endpoints. If you use 0, that means you have a rectangle with no width. It doesn't go left or right. It's just right at 0. So the left endpoint is meaningless. The right endpoint of pi, also meaningless, because if you go all the way out to pi, if you remember that original graph, the cosine curve is 0, which means you'd have no height to your rectangle. So 1.7 is the only one that can work. Plug it all in, you get an area of 2.2. And there we go. Thanks for coming. That's applied optimization. Have fun. Story problems are so much fun.